Whoever said you can't get something from nothing must never have learned quantum physics. In empty space, the epitome of nothingness, simply manipulating it correctly will cause something to appear. When two particles collide in empty space, sometimes additional particle-antiparticle pairs emerge. At the subatomic level, if you try to separate a meson's quark from its antiquark, new particle-antiparticle pairs are pulled out of the space between them. In theory, a strong enough electromagnetic field can even create particles and antiparticles from the vacuum itself, without any initial particles or antiparticles. It was previously believed that the highest particle energies were required to produce these effects, achievable only in high-energy particle physics experiments or extreme astrophysical environments of cosmic strength fields, such as those around magnetars, or created transitorily during high-energy collisions of charged nuclei. However, in recent years, strong enough electric fields were created in a simple laboratory setup, using the unique properties of graphene, enabling the spontaneous creation of particle-antiparticle pairs from nothing. This prediction, made over 70 years ago by one of the founders of quantum field theory, Julian Schwinger, has now been verified. The Schwinger effect shows us how the universe can truly create something from nothing. The nature of the universe has long fascinated scientists and philosophers alike, leading to a ceaseless quest to understand the fundamental constituents of reality. It's easy to be captivated by the face nature reveals directly to our senses. However, the evidence gathered from our rudimentary perceptions often yields a clouded conception of the world we inhabit. Modern science paints a very different picture. Breakthroughs in physics have forced and continue to force dramatic revisions to our understanding of the cosmos. The overarching lesson that has emerged from scientific inquiry over the last century is that human experience is often a misleading guide to the true nature of reality. Lying just beneath the surface of the everyday is a world we'd hardly recognize. The universe doesn't consist of static things, but dynamic fields. What truly matters are the ongoing happenings, processes, and occurrences, rather than concrete substances or entities. Ultimately, nothing simply is. Rather, everything happens. The universe, in other words, is in a constant state of flux and becoming, rather than stasis. As it turns out, space is unavoidably suffused with quantum fields. Far from being inert, empty space is now understood to harbor latent energies and phenomena that manifest under certain conditions. The universe, with all its complexity, can be reduced to its simplest, most fundamental components. If you can determine the underlying rules, laws, and theories that govern reality, you can use this understanding to predict what will happen both in the distant future and the distant past, based on the current state of your system. The quest to unlock the secrets of the universe is about meeting this challenge, identifying what makes up the universe, understanding how these entities interact and evolve, and solving the equations that predict outcomes not yet measured. In this sense, the universe makes a lot of sense, at least conceptually. However, when discussing the actual components of the universe and how the laws of nature work in practice, many people struggle with the counterintuitive nature of quantum mechanics. In the universe we inhabit, it's impossible to create and achieve absolute nothing in a truly satisfactory way. Everything, at a fundamental level, consists of individual entities, quanta, that cannot be broken down further. These elementary particles include quarks, electrons, the electrons' heavier cousins, muons and taus, neutrinos, their antimatter counterparts, photons, gluons, the heavy bosons, and the Higgs. Even if you remove all of these, the empty space that remains isn't truly empty in many physical senses. Firstly, quantum fields still remain even in the absence of particles. Just as we cannot remove the laws of physics from the universe, we cannot remove the quantum fields that permeate it. The vacuum is a state with the lowest possible energy, but not zero energy. This vacuum is permeated by quantum fields, which can give rise to particle-antiparticle pairs that briefly pop in and out of existence. Secondly, no matter how far we move any sources of matter, two long-range forces still remain: electromagnetism and gravitation. While we can create setups that ensure the electromagnetic field strength in a region is zero, we cannot do the same for gravitation. Thus, space cannot be entirely emptied in any real sense. Even for the electromagnetic force, if you completely zero out the electric and magnetic fields within a region of space, experiments have shown that empty space isn't truly empty. If you create a perfect vacuum, devoid of all particles and antiparticles, where the electric and magnetic fields are zero, there's still something present in this region of what might be called maximum nothingness. By placing a set of parallel conducting plates in this region, you would expect them to experience only the force of their mutual gravitational attraction. However, the plates attract each other by a much greater amount than gravity predicts. This phenomenon is known as the Casimir effect, and Steve Lamoureux demonstrated it in 1996, 48 years after Hendrik Casimir calculated and proposed it. Let me explain what the Casimir effect is. You see, Hendrik Casimir's idea for the experiment was simple. Place two uncharged metallic plates extremely close together in a vacuum and wait. Spontaneously, as if by magic, the plates will be drawn together. No external forces, no pushes or pulls, no action of gravity, tension, or magnetism. The objects simply get attracted to each other. Why does this occur? The phenomenon is explained by the quantum properties of the vacuum itself. What we perceive as empty space is filled with fluctuating electromagnetic fields. These fields create a sea of virtual particles that constantly pop in and out of existence, as stated earlier. When two conductive plates are placed very close to each other, they restrict the wavelengths of these virtual particles that can exist between them compared to the space outside the plates. This imbalance creates a pressure difference, resulting in an attractive force pushing the plates together. We don't normally see, sense, or experience the Casimir effect. However, this effect becomes significantly important when dealing with micro and nanoscale devices. When designing micro and nanoscale machines, engineers and scientists must account for all forces that could influence the behavior and functionality of these tiny devices. The Casimir effect is one such force that, despite being negligible at larger scales, can exert a considerable influence at the micro and nano levels due to the small distances involved between components. For example, researchers have developed microscale sensors capable of detecting and analyzing the flow of chemicals on an extremely precise molecule-by-molecule basis. These sensors rely on the precise movement and interaction of their components. If the Casimir effect were not taken into consideration during the design phase, the unexpected attraction between parts of the device could lead to malfunction or inaccuracies in sensor readings. Moving on, in 1951, Julian Schwinger, a co-founder of the quantum field theory that describes electrons and electromagnetic force, provided a complete theoretical description of how matter could be created from nothing by applying a strong electric field. Although Fritz Sauter, Werner Heisenberg, and Hans Euler had proposed the idea in the 1930s, Schwinger did the detailed work to specify the conditions under which this effect would emerge. As a result, it is primarily known as the Schwinger effect. Normally, we expect quantum fluctuations in empty space, excitations of any and all quantum fields present. The Heisenberg uncertainty principle dictates that certain quantities cannot be known simultaneously with arbitrary precision. These quantities include energy and time, position and momentum, orientation and angular momentum, voltage and free electric charge, electric field and electric polarization density. While the uncertainty principle is usually expressed in terms of the first two pairs, its other applications can have equally profound consequences. Remember, for any force in existence, we can define it in terms of a field, where the force acting on a particle equals its charge multiplied by a property of the field. When a particle moves through a region where the field isn't zero, it can feel a force, depending on its charge and sometimes its motion. The stronger the field, the greater the force, and consequently, the more field energy exists in that specific area of space. Even in completely empty space, with no external fields present, there's still some amount of non-zero field energy existing in any region. If quantum fields are everywhere, according to Heisenberg's uncertainty principle, there will be an inherently uncertain amount of energy present in that region over any chosen duration of time. The shorter the duration we observe, the greater the uncertainty in the energy amount. Considering all possible quantum states, we can envision fluctuating fields and particle-antiparticle pairs that sporadically appear and disappear due to the universe's various quantum forces. Let's say we increase the electric field. As it gets stronger and stronger, what happens? First, let's think about a simpler case, a meson, which is made of a quark and an antiquark. They stick together because of the strong force and gluons. Quarks have 6 flavors: up, down, strange, charm, bottom, and top. Antiquarks are just opposites with opposite charges. Sometimes the quark and antiquark in a meson have opposite charges, either plus 2/3 and minus 2/3 for up, charm, and top, or plus 1/3 and minus 1/3 for down, strange, and bottom. If you put an electric field on this meson, the positive end and the negative end will pull in different directions. If the field is strong enough, they can pull far enough apart to make new particle-antiparticle pairs from empty space between them. This means we end up with 2 mesons instead of 1, and the energy needed to make the extra mass with E equals mc² comes from the electric field energy that pulled the meson apart in the first place. Now let's think about an extremely powerful electric field, much stronger than anything we could create on Earth. Imagine condensing a full coulomb of charge, around 10 to the power of 19 electrons and protons, into tiny balls, one purely positive and one purely negative, and separating them by only a meter. In this region of space, the quantum vacuum would be highly polarized. Strong polarization means a significant separation between positive and negative charges. If the electric field in a region is powerful enough, when you create a virtual particle-antiparticle pair of the lightest charged particles, electrons and positrons, there's a chance they'll be separated so far by the field's force that they can't come back together and annihilate. Instead, they become real particles, drawing energy from the electric field to conserve energy. This process generates new particle-antiparticle pairs, and the energy needed for them, via E equals mc², decreases the strength of the external electric field accordingly. That's what the Schwinger effect is all about, and it hasn't been observed in a lab yet. It's mostly thought to happen in the most extreme astrophysical environments, like around black holes and neutron stars. But even then, it's still just a theory because these places are so far away. On Earth, the strongest electric fields we've made are in laser labs, but even with the most powerful lasers, we're nowhere near strong enough. Normally, in conducting materials, only certain electrons can move freely and contribute to conductivity. But if you could create really strong electric fields, you could make all the electrons flow. In January 2022, researchers at the University of Manchester used a smart setup with graphene, a super strong material made of carbon atoms, to achieve this with a relatively small magnetic field that's easier to work with in experiments. And in doing this, they saw the Schwinger effect happen. They made something like electron-positron pairs in this quantum system. Graphene is quite unusual, especially because its sheets behave like a 2-dimensional structure. This reduction in dimensions limits the options for the quantum particles inside and the quantum states they can occupy. In a study, researchers used a graphene-based structure called a superlattice, made of multiple layers of materials arranged in periodic patterns. They applied an electric field and observed a unique behavior. Electrons not only flowed from the highest partially occupied energy state, but also from lower, completely filled bands. This led to various exotic behaviors in the material, including a first-ever observation, the Schwinger effect. Instead of creating electrons and positrons, it produced electrons and their condensed matter equivalent, holes. Holes are where an electron is missing from a lattice and flows in the opposite direction to the electrons. The observed currents could only be explained by this spontaneous production of electrons and holes, matching Schwinger's predictions from 1951. There are various methods for exploring the universe, and quantum analog systems are among the most potent tools for investigating exotic physics. These systems employ the same mathematical principles that describe inaccessible physical realms, but can be created and studied in a laboratory setting. Testing the Schwinger effect in its pure form is challenging, but graphene's remarkable properties, such as its ability to withstand immense electric fields and currents, allowed it to manifest for the first time in any form within this specific quantum setup. As co-author Dr. Roshan Krishnakumar noted, when we first saw the spectacular characteristics of our superlattice devices, we thought, wow, it could be some sort of new superconductivity. Although the response closely resembles those routinely observed in superconductors, we soon found that the puzzling behavior was not superconductivity, but rather something in the domain of astrophysics and particle physics. It is curious to see such parallels between distant disciplines. With electrons and positrons, or holes, emerging seemingly out of thin air, torn from the quantum vacuum by electric fields, the universe showcases the seemingly impossible, creating something from nothing. We don't live in a universe where matter floats around in empty space. We live in a universe of energy fields that spread throughout the universe and interact with one another, creating everything we see in the process. When contemplating the vastness of nothingness, the infinite void, death, it's astonishing how the concept of nothing can evoke such fear. William Shatner, at the age of 90, embarked on a space journey anticipating to encounter the mystery of the universe, only to find there was no mystery, no majestic awe to behold. All I saw was death. I saw a cold, dark, black emptiness. It was unlike any blackness you can see or feel on Earth. It was deep, enveloping, all-encompassing. Yet, in another paradox of nothingness, Shatner wasn't truly observing a void. Rather, he was looking at a vacuum where, at that very moment, a lot was happening that he couldn't see. Quantum field theory stands as one of the most successful theories in physics, renowned for its remarkable accuracy in predicting the outcomes of diverse experiments. According to this theory, our universe doesn't consist of matter floating in empty space. Instead, it is a universe of energy fields that permeate space and interact, giving rise to everything we observe, including ourselves, as we are an integral part of these fields. Some physicists describe these fields as fluid-like, akin to water in a swimming pool, while others liken them to a room filled with varying levels of energy, much like a field of distributed heat. These fields are in constant motion due to quantum fluctuations, brief changes in energy resembling ripples in a wave, caused when external forces excite the particles within the field. For instance, an electromagnet can induce changes in an electromagnetic field. Even in their lowest energy state, known as the vacuum state, the fields exhibit continuous activity. Pairs of positive and negative particles continually borrow energy from the vacuum, briefly materialize, and then vanish, returning energy to the vacuum. These ephemeral entities are termed virtual particles. When the field is excited or reaches a higher energy point, it has ripples or waves that create elementary particles that are not canceled out. It is these particles that remain, interacting with one another, that creates the world we know. The particles created by the field are contingent upon the type of field in question. There are different matter particles, each associated with specific types of fermions. Electrons, up quarks, down quarks, fundamental constituents of all atoms, and neutrinos being examples. Additionally, these fermions interact through three types of fields: electromagnetism, which involves photons as its particles, the strong nuclear force, which features gluons, and the weak nuclear force, with W and Z bosons as its particles. According to Cambridge theoretical physicist David Tong, without fields of force, matter particles would essentially drift aimlessly in the universe, devoid of interactions and lacking any interesting behaviors. Then, there's the Higgs field, likened by Tong to molasses spread throughout the universe. The Higgs field imparts mass to other particles, preventing them from moving at the speed of light. Tong acknowledges that this metaphor is imperfect because it implies friction, whereas in reality, various particles interact with the Higgs field in distinct ways. All the fields, including matter and force fields, are present everywhere, but they interact in diverse ways. Some particles within these fields completely disregard each other, while others interact, giving rise to reactions and complex structures. The collaboration of these fields encompasses everything we comprehend and observe, as well as much that remains unknown and beyond our perception. Strangely, the creation of particles that constitute matter is an exception. For instance, an atom comes into existence when there's enough energy in the quark fields to produce quarks that aren't annulled by antimatter quarks, although the reason for this occurrence is not fully understood. Gluons, which are particles associated with the strong force, bind with two up quarks and one down quark to form a proton. Subsequently, gluons link protons with neutrons, creating a nucleus. Physicists theorize that the visible universe comprises remnants that manage to endure the constant creation and destruction of virtual particles. However, it's worth noting that the particles constituting dark matter present a separate and distinct matter. Even though the universe is teeming with virtual particles, it doesn't entirely dismiss the concept of nothingness. Firstly, there's the mystery of the nothingness preceding the Big Bang, a realm we are yet to comprehend. Moreover, the nature of this nothingness, comprising vast fields of quantum energy, appears to be something that yields a combination of ingredients, namely matter and force, culminating in the creation of our world. Physicists remain uncertain about why, following the Big Bang, certain elemental particles managed to endure. In his book, A Universe from Nothing, theoretical physicist and cosmologist Lawrence Krauss suggested that the answer lies in the evidence. The inherently unstable nature of nothingness gives rise to elementary particles. There's also the possibility that the entire universe is just one big virtual particle. The vacuum genesis hypothesis theorizes that the entire universe began as a big fluctuation in the nothing that came before it. While it hasn't been proven, it sure is an interesting idea to think about. That in the end, all we, you, me, the whole universe, add up to is a big bunch of nothingness. No matter how vividly you can imagine an empty universe with absolutely nothing in it, that mental picture doesn't align with reality. Insisting on the validity of the laws of physics is sufficient to discard the notion of a genuinely empty universe. As long as there is energy within it, even the zero-point energy of the quantum vacuum is enough. There will always be some form of radiation that cannot be eliminated. The universe has never been entirely devoid of content, and as long as dark energy doesn't completely decay, it never will be either. The universe is the way it is, and while we endeavor to comprehend it to the best of our abilities, we must remain humble in the face of the vast cosmic unknown. The only advice I can give you is this: embrace the curiosity that drives us to explore, question, and uncover the mysteries that continue to unfold. And that's it for the video. I really hope you enjoyed it. Thanks for watching, and check out this video where we talked about a radiation that may be faster than light. It's on your screen.